Recording and welcome, ladies and gentlemen, to the big show. No, I'm just kidding. Okay, so today we're going to start with something called binary trees. Now, we kind of is everybody okay seeing that screen, right? You already said you're good.
Mm-hmm.
Yep.
Okay.
Yeah, looks good.
So we've talked about something like this earlier, and what I'm talking about is we did something over here. We've done doubly linked list where I have a node, and with the node comes 2 pointers. And before the 2 pointers, one was prev and one was next. And we had this nice linear layout, and we drew a picture. We drew it across the whiteboard in the classroom. But today we're going to enter basically a whole new realm of what we can do. And what I mean by that is the whole searching and sorting and things like that, we can do a whole lot faster once we start taking a look at this layout. If you remember searching, we had the linear where we started at the first one, we went to the second one, the third one, and we were doing some searching. When we did the binary search, we started in the middle and we did this whole higher and lower thing where we kept cutting it in half. And somebody tell me, when I had 1,024 elements, how many guesses did I need to get it right?
1,024.
Nope. That was for the linear. But
For the binary, it
that.
really has it.
binary was how many?
16?
No. 1,024 was 2 to the
No.
2 to the 8th power.
little higher. Little higher. Use your fingers if you have to. 2 to the 10th power. So it took 10 guesses. So now when you're starting to do this big O notation, which you all are working on, you knew that worst case scenario would have been 2 to the 10th power. Well, this binary tree is now going to bring in something called log 2 of n power, where it should sort faster than that. And we'll slowly start to see how that plays out. But what we're dealing with today is right here, a binary search tree. And we're going to start with some terminology. And over on the left side of your page, you can see we have child nodes. Well, up at the top, I have a root pointer to the first node. And that's this node right here. It's called the root. Okay, so I'm always going to start with a root. From there, as I add elements, I'm going to go either to the left or to the right, depending on the value. Is the value less than or is it greater than? All right, so some terminology. Child nodes. Well, the root has 2 children. Everybody would have 2 children moving the way down. So if there's child nodes, there's also going to be a parent node. Okay, we have a left child and a right child. That's kind of self-explanatory. The whole thing is called a tree. When I start talking about subtrees, I'm looking at this kind of region. I'm making it really light because I thought it was okay. So that would be a subtree. In fact, we would say that's the left subtree of the node, yada yada yada, whatever I put in there. Okay, these guys down at the bottom, what do you think they're called? Well, the last term we have is leaves. So why are these called binary trees? Well, if I took the whole thing and turned it upside down, well, down here's the root in the ground and the tree grows up and the leaves are on the end. So the terminology basically is because it resembles an upside down tree. See, that's something I couldn't do on the whiteboard if I wanted to. All right, so I have a tree, and the discussion is now, how do I make a tree? How do I lay this out? How does it make searching go faster? Why is it called binary? Well, again, it's called binary because I have a left or a right, a 0 or a 1. Somewhere down the road, we're going to take a look at taking this node, which has 1 key in it and 2 pointers. And what if I said, well, can I put more in there? Can I put 3 keys and 4 pointers and different? And we'll look at that down the road. But for now, when I only have 2 options, we're going to go with the term binary search tree. So now let's take some letters. Somebody give me some letters. Just random letters of the alphabet.
COVID.
CMCOVID. Okay, so I'm going to build a search tree with these, which means when I create this binary search tree, I'm going to throw an element in, and when I'm all set and done, I should be able to search quicker. All right, the first letter is an M, so M's going to be up top. That's going to be my root. Okay. Next letter is C. Which direction would C go?
Left.
To the left, because it's less than. Now, when I'm drawing these, I've learned over time to make them go wide because I'm going to keep going down from there. Next letter would be
Oh.
O to the
Right.
right. Next letter would be
V.
V, which is to the.
Right.
Who gave me two O's? We'll make that a D.
Mhm.
V would go to the right of M, to the right of
Oh.
O. Okay, I.
Left and right.
To the right of C.
Mhm.
Okay, D.
Left, right, left.
To the left of I.
Yep.
Okay, so we just built a binary search tree. Let's see. I talked about this log-based to event. Did anybody see this when you were doing your big O notation?
Mhm.
Mm-hmm. Yeah. Mm-hmm. Okay, that means no. We'll have to talk more about that later. All right, let's take a look. If I'm looking for a letter, give me a letter. Pick any random letter. I want to see if it's in my search tree. What do you get?
X.
X. X is greater than M. X is
Greater than.
greater than O. X is
Less than B.
less than V. It's not found because what would be to the left here? A null.
No.
Okay, so it's not found. So it took me 3 searches to see if X was on this list. All right, so let's start talking about some questions, some other things. M is my root. What is the height of this tree? New term. Height of this tree. Take a guess.
4.
4, right? And that's what I go by with 4. Now, I've seen books that say the height would be 3. It's the levels after the root, but I'm going to go with 4 because that seems to be what comes natural. That's what I've seen the most of. All right. If I have a tree of height 4, how many items could be in that tree if they were all filled up? Does
2 to
everybody
the 4th
understand?
power.
2 to the 4th power. So you're saying 2, 4, 8, 16. So one possible guess is 16. I'm going to slide this up, see if it makes it a little easier to read. Does that help? One guess was 16. Somebody have another guess? This actually goes back to your pre-calc with sequences and series and so on. If I have a height of 1, that means I have a root. There's 1 item. The next level would be what? 2 items? That would now give me a total of 3. The next one would have as many as, how many items?
How many?
4. So that now gives me a total of 7 things to go in there. The next level would have how many possible items? Well, I'm starting to see a pattern of 1, 2, 4. So my 4th level would have how many possible items in it?
8.
8, which tells me my tree would have 15 things. So 16 was off by 1. So I could have as many as 15 things in this. Now, how long would it take me to search? Well, you got the idea. I'm just coming down, checking, and moving left and right as I go. Any questions?
No.
That's fine.
Yes, no, everybody's okay?
So
All right,
wait,
go ahead.
how did they get? I still quite didn't get like the 15, 16 thing. So basically,
Okay.
that's the leaves of the things.
No. Here's what happens. If I'm at level 1, well, let's go to a new page. It's a good question. If I'm at level 1, how many items? Ooh, there we go. 1 item, right?
One item.
If I have level 2, how many items are there total?
3.
Yep. And Vasily actually had an equation for it. Now I'm up to 7. If I went to a height of 4, how many total items are there?
This increases. Okay.
2, 4, 6, 8, 4, 2, and 1. 8, 4, 2, and 1.
So that's basically the 2 to the power of whatever. It just is
Right.
those are just the powers of 2.
2 to the power of however many levels there are minus 1.
Yep.
Because this gave me a total of 15 and it's 4 levels.
Yes.
Okay.
Got
All right. So taking a look at this now, I'm starting to think, let's go back to when we first learned about linked list. And if I want to get ready to work with the binary tree, what functions might I need to fill or work with a binary tree? Well, I'll give you the first one. I want to see if it is empty,
Mhm.
right? If it's empty, I know my head pointer, which is at the top, would point to what?
the 2 point.
No.
To null.
Okay.
So that's real easy. Whoever volunteers to write is empty can always say, oh yeah, I'll write is empty. Does head pointer equal null? Or you could just do the if not head. Remember, we've used that a couple of times. If not head. So we're stealing it from something that we've learned before. Okay, some other things. Is empty. I don't know if I need is full, but what were some of the more common ones we had? Starts with an I.
Insert.
Insert. Along with insert, insert's best friend was
Delete.
delete. We may need to figure out how to traverse through here. So traverse is going to be a big thing coming up. Okay, and when I look at this, there's actually going to be several ways to traverse through a binary search tree. So is empty was a piece of cake. Insert. Start talking about how I would insert. And we're just going to make a couple of basic notes, and we're going to then go and look at some code that I'm going to ask you to go to D2L and look at in a couple of minutes. But insert, well, let's see. I'm going to take a list of numbers again. Let me ask you this. Would this be a good list of numbers? A, B, C, D, E.
Not in the
Why would A, B, C, D, E be bad?
because it's progressing steady.
Yeah, it would look something like this. A, whoops, excuse me, B, C, D, E. And that's a problem, right? There's no benefit to doing that way. Later, we're going to look at how we can, if we ever do get A, B, C, D, E, how can we balance it to make it look a little bit nicer? So yeah, we don't want something that runs down the side. So let's just get that out of the way. What if I just took a word like, somebody give me a word.
Train.
Train. Okay. So I'm going to get ready, and if it's empty, I need to put the T at the top. Okay. Now what? So my next letter is R. It's not empty. So what do? I have head here pointing down. I'm doing some work with insert. Head points to T. Now I'm getting ready to insert the R. So what do?
Goes
Compare
to
it
the right.
to the letter, yeah.
Yep. So I'm going to take my R and compare it to this guy's value. And if R is less than, I go to the left to see if it equals what. So right now I put T in. This guy equals null. This guy equals null. Next letter I want to put in is the R. So I check this value. If it's less than, where do I go? Down this side, right? So then I would come to whatever's here. If what's here is null, then I let the left pointer equal that new node, that R. If it goes this way, I let it equal this guy. Well, all right, so let's put put R in. So now I have T, and R goes to the left, and I have R in. Now, when I create the new node, remember these guys are both going to be null. So this is a null, this is a null, and this is a null. Is everybody okay with me abbreviating null with just ends? Yeah. Okay. My next letter I'd want to put in is A. So I'm going to check T, see if I need to go to the left or to the right. Move to the left. Is it empty? If this is null, then I insert it, right? If it's not, what do? I check to the left or I check to the right. Once I check which way I go, I check to see if it's null. If it is, I insert it and done. Otherwise, I check to the left or to the right. Once I'm there, I see if it's null. If not, I check to the left, to the right. Everybody see what's happening over and over and over. Give me an R word.
Range.
Rain, no. Rain. Rain makes corn. No. R word. Recursion. Thank you. So something's happening over and over and over where I see a pattern happening and it's going recursively. So I'm wondering, and I already know the answer to this, if I could make this insert function recursive. All right. So now I'm going to put my recording on pause because I want you to go and load up, and it's on D2L. It's what I gave you for today. Run program 20-1.
20 or 21?
21, excuse me. Okay. So I'm back recording. We have program 21-1. And you see I am creating an int binary tree. This is my class, creating an object called tree. And it looks like I'm going to insert a 5, an 8, a 3, a 12, and a 9. Do you notice instead of letters, this time we're doing numbers? We could do structs if we want to. And then we would just pick one of the fields in the struct to decide how we want. So we could put a lot of different things in this tree if we wanted to. Going to the header file. Let's see what we have going on here. I have private member functions, and the only one we're interested in right now is insert. Okay, so hold on a second. I'm looking at line 7, and I'm saying private, and down here, I made this function private. Somebody say, Okay, but if I remember back in 21-1, the program, I'm calling a function called insert node. So let's go back up here and see if I can find, there it is in my public, I have the function called insert node. All right, so I wonder what's going on here. I say void insert node, and it looks like I'm bringing in the number that I want to insert. Everybody's with me? Yep. Okay, so let's go to our implementation file, and I'm going to go to insert node, which is right here, line 27. Everybody can see my screen?
Yes. No.
Yes. Or you're looking at your own?
Yes.
I see,
Are you
I'm going to insert the number. So this is my function, but inside of this function, I have a pointer to a new node. Okay, I have, so let's see, I have a pointer for my tree, and I have a pointer for my new node. Does that sound correct? So when I went back up to this one I was talking about a minute ago, insert, I have a pointer to a tree node, which is my actual tree, and I have a pointer to the node, which is my new node. So when I'm going to do this recursively in a minute, you're going to see why I need to keep passing pointers. Okay, going back to the implementation file, I come in and I say, all right, I have a number that I'm bringing in that I want to insert into the tree. I create a new node. I fill the values, including the left and the right, pointing to null. Now I'm going to insert. This time I'm passing in the root to start and where the new node is. Everybody's with me? Okay, so now I'm going to go back and I'm going to say, so this is where I want this insert, because I just called it and I'm passing in references to the two different nodes. All right, now let's go find insert. Remove, delete, make deletions. Where's insert? Did I pass it? Should be at the top. That would make sense, right? So insert comes in, and you notice I'm pointing to two different tree nodes. Right now it's the header and it's the new node. Okay, if node pointer equals null, good, I took care of the header. If it was empty, I didn't even have to check if it equals null, then I insert that new node. Capiche? If I have to traverse down the left because it's less than, I call insert recursively, and I'm sending in where node pointer's left is, and again, I'm sending in that new node I want to add. If it needs to go down the right, I call insert with node pointer's right pointer and new node, so that it's going to recursively keep going until I find a null, and then it'll insert it. So that whole moving left and moving right all of a sudden now looks pretty simple. Questions? So right here below it, in my function insert node, I create a new node and I call insert. First time I'm sending root in and new node. If it's empty, meaning it points to null, then that node pointer gets a value of new node. Otherwise, depending on what the value is, if I have to go to the left, I take the current node pointer and go left and send new node in so that it recalls insert. Nice and easy. I don't need a while loop. I don't need a whole bunch of other stuff going on. Questions?
Nope.
What if you have duplicate letters or numbers?
So let's decide right now, where do they go? Where do you want them to go? Duplicates can go to the
Left.
Good. We'll go to the right with any duplicates. Now, actually, that's where we do go. We go to the right. So if you have matching duplicates, you go to the right. That's the common standard.
Is it just like the horizontal line? Like meaning to the right sort of thing?
Well, with the doubly linked list, we really didn't see any repeats. We were working with a unique homogeneous list. But now we'll be able to have some repeats going on. Okay? All right. So now the next thing I want to take a look at is, let me go back to here, and I want to jump to my other camera. Ta-ta! Everybody can see it?
Yep.
All right. So let's say I have a list, okay? And I want to be able to, well, I don't want to hit delete yet. Delete's going to go crazy. But I want to be able to traverse it, as long as I don't drop my pencil. I'm going to take a word like, I can't do, I was going to do coronavirus, but let's stay with Harrisburg. Okay, we have a couple of repeats. And if I get ready to build the tree with Harrisburg, it's going to be an H, and then A goes to the Oh, to the left. R to the right. So far, so good.
Yep.
R is to the right. Where's I go?
To the left, or to the right of, oh, no. R, yeah, left.
Okay. There's I. S.
To the right of the smaller I.
Bigger than H. Q, R, S. It's bigger than R, right?
So there's another R. So
It's bigger than the R. So it's going to go out here.
how do we, yeah, okay.
Okay. B.
It goes to the right of A.
Okay. U.
To the
After S.
right of S.
Right of S. Another R.
R.
It goes to
Is it to the left of R?
no. Oh, go down to S and then left of S.
Got it. Excuse me. And finally, G. Thank you. And finally, G.
Let's see.
Okay. That's
It goes to the right of B.
To the right of B. I didn't give myself much room. G. Okay. So that and that and that. Those would be null. That would be null. Both of these would be null. How many nulls are there?
1, 2,
1, 2, 3, 4, 5, 6, 7. I get more than 7. Oh, there's 2 here with G.
Oh, yeah.
11.
I heard an 11. Okay. Can I get somebody agreeing with that?
Yeah.
1,
Yep.
2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So if there are 11 nulls, how many leaves are there?
Ooh, good.
What's a leaf? A leaf would be
5 squared. 20.
somebody said 4. A leaf would point to how many nulls?
2.
2 nulls. Yeah. Okay. So we got some terminology going. All right. So now we have Harrisburg, and I want to talk about traversing. And there's a couple different ways to traverse through this list. And this is going to be a topic that some of you have seen in CPS 230, and some of you have not seen, but will when you get there. Now, to traverse this, we can go one of 3 different ways, okay? And I'm going to start with something really simple. I'm going to start with 4 plus 2. And it sounds kind of weird, but we're going to talk about a constant 4, a constant 2, and an operator 3. And I'm going to create a binary tree that looks like this, okay? 4 plus 2. Now, when you get to 230, or if you remember, you got the idea of I'm building a binary tree for this. Not necessarily for searching, but I'm just building a binary tree. All right, so what do I have? A left child, I have a right child, and I have what we're going to call node up here. So this guy is left, this guy is node, and this guy is right. Now, when it comes to a simple expression like 4 plus 2, we can do 3 types of traversals. Does anybody remember what they are? No.
In order.
Yeah, in order is 1. Give me another one.
Pre-order.
Pre-order. And finally,
Post-order.
post-order. Okay. Does anybody know the other name for post-order? This is really out there.
Postfix?
Polish notation.
Polish notation.
Polish notation. Okay. So pre-order talks about putting the node first. So pre-order means the operator would come first. So in pre-order, I would have for pre-order, I'm going to have the plus, the 4, and the 2 because my operator comes first. So when I get ready to write this up, the plus was my node, and then I went to the left, and then I went to the right. In order, where's the plus? It's in the middle. Everything's in order. So what was the order of my 3 letters here? It was my left, my node, and my right. And then finally for post, 4 to plus, and now I'm going to remind some of you in 230. Tell me what I'm doing. Push, push, pop, pop, add, and push. I was working with a S word.
A stack.
Stack, very good. So this guy is going to be left, right, and then node. Left, right, and then node. Okay, so you notice the only thing that moves is the node. Here are the nodes in the beginning, here are the nodes in the middle, and here are the nodes at the end. So we have pre-order, in order, and post-order. Okay, so now we're going to apply these 3 different ways to traverse up to our binary search tree up above. All right, let's see what we can come up with. So I always go back to something simple if I have to help me build this chart. Okay, so now I want to do a pre-order traversal of my tree. So the pre-order starts with the node. So I'm at my node, which is H. So I go H. My next movement in pre-order is to go to the left. When I get to the left, I'm at a node. So I go A. Then it says in my pre-order, once I'm done with the node, move to the left. Well, I can't, there's nothing there. So now I go and move to the right. I'm at a node. So I put B. Now I go to the left. There's no left. So I come back to the node and hit the G. It's a node. I check its left. Nope. I check its right. Nope. So now I start bumping all the way back up to the H. So I took care of the node for H and I took care of its left. Now I need to take care of its right. When I come over to the right, I get R, which is a node. I check its left, which is a node. I check its left. There's nothing there. I check its right. There's nothing there. So now I'm bumping all the way back up to the R. I'm done with the node. I'm done with its left. So I come right. Bam, I hit that R. I check its left. There's nothing there. I've already done the node, so I move to its right. Bam, I hit the S. It's a node. I check its left, which gives me an R. I check its right, da-da-da, go back up, finally U. So a pre-order traversal of this would be HABGRIRSRU. Say, okay. Once again, do you notice any kind of recursion going on?
Yeah.
Yeah. All right, let's blow your minds. Y'all give it a try on the in order, see what you get. This time you're going to go to the left first. Every time you hit a node, you move to its left if you can. Keep moving to the left. Once you take care of the lefts, then you back up, take care of the nodes, then you move to the rights. First letter.
A.
A, very good. I started at the H. I don't do the node first. I move to the left. I'm now at the A. I move to its left. I can't. So now I go back up and do its node. Now I move to the right, which is here at the B. Can I go to its left? No. So I come back up and hit the node, and I move to its right, which is G. Can I move to the left? No.
No.
So I come back up to the node and I move to the right. There isn't. So now I go back up, back up, back up. The next thing should not. So I took care of all this left. So now I go to the node, which is H, and then I move to its right. Once I come to a node, I try to go left. If I can, I go left. If I can't, I hit the node. What's the next letter after H?
R.
I.
I, right? Because I moved to the R, but I don't do the node yet. I do the left. I come here, I have a node. I check the left. Nope, can't do it. Come back, do the I. Try to move to its right. Can't do it. Come back up. Move back up to the node. So after that I is an R. Come to the next one. Can I move left? Nope. Can I do the node? Yep. Now I move to its right. Go to its left. Go to its left. Nothing. Go to the node, which is R. Go to the right. I can't. Go back up to the node. S. And finally U. What do you notice about in order?
It's alphabetical.
It's alphabetical. It's sorted for us. Ha. So I did in fact build the tree correctly. So that's kind of if I asked you on a test to do in order, you can just sort of, you know, rate it alphabetical. I know some of you have already started. Let's see what you can do with postfix.
Okay. I guess the next one is G
So where are we starting here? The first one is G.
from A.
So we're going to go to the left and we hit A. So what's your overall guess, Vasily?
It's probably completely wrong based
That's
off
okay.
how I did AGBHIRRRUS.
Anybody else have a guess? Some of you do. You're just afraid to say it.
I got ABG
Yeah?
RIRSRUH.
RIRS.
SRUH. I think it is.
Okay. Somebody else have a guess?
I got ABGIRRSUH.
You missed an R in there.
Oh, yeah, sorry. Yeah. I would have put it in order with the rest of the R's, but
Right. Okay. Let's see what we got. So back up here in the pre-order, I went node. And when I hit it, I displayed it and moved to the left. Okay. So let's start down here in postfix. When I come here, I go to the left. Okay. So I go to the left, there's nothing. I go to the left, there's nothing. Now I come back up and I go to the right. I try to go to the left, there's nothing. So I come back up and I come to the node. I try to go to the left, there's nothing. I try to go to the right, there's nothing. And now I hit the first node. So I would hit G. Okay, remember, whenever I hit a node is when I displayed it. So I'm going to do all of my left and rights first. I come to the left. I come to the left. Done with lefts. I go to the right. Can I go left? Yeah, no. Can I go right? Yes. So actually the first one should be a G. You with me?
Okay.
Okay, so I took care of the node. So now I come back up here. I took care of the left. I took care of the right. Now I take care of the node. Then I come back up to this one. I took care of the left. I took care of the right. Now I have the node. I come back up to here. I took care of the left. So now I move right. I come to here. I move to the left. I come to here. There's no left. There's no right. Now I take care of the node. I come back up to here to the R. I took care of its left. So now I move to the right. I check out its left. There's nothing. I check out its right. I'm at a new node. I check out its left. I check out its left. I check out its right. So it's that R. Come back up here. I move to the right. Now it's going to be the U. Basically, I'm now going to go S, R, R, H. S, R, R, H.
Wow.
Got it now? So some things that came out of that was I only print when I hit the node. Okay, I keep moving left as much as I can. Then, you know, I check out the rights. When both of those are done, then I finally hit the node. I keep moving left till I stop. Then I go back and I start moving right. Keep thinking I'm going to move left and then back up. Left's done, right's done, boom, node. Left's done, right's done, node. Left's done, right's done, node. Left's done. Now I start down the right side. Questions?
Yes. So while this is great for sorting and searching, using binary trees and using this, is there any actual way to get back to the original data you had, or is it impossible to actually know how to get back to what you had?
You mean how you inputted Harrisburg with the H, the A, the R, the I, S, B, U, G?
Yeah, so is there any way to, with our letters that we now have outputted, is there any way that you could actually get it back to Harrisburg?
No. Nope. I mean, that would be something you'd have to store in an array, a regular array, if you needed to have it when you come back.
Gotcha.
Okay. I'm going to pause it. I want everybody to jump over and load up 20-2, and we're going to take a look at the code for these three traversals. Okay, I'm guessing everybody's here because you're faster than I am. And so we have the inserts, and then I have three traversals. I have the in order, the pre-order, and the post-order. Remember the in order, the node's in the middle, so it should be left node right, which means if I run this, crossing my fingers, that my first output should be sorted. Somebody tell me that worked.
Yeah.
And
Got
there it
no
is,
error.
3, 5, 8, 9, and 12. Okay, so let's go back to the header file, and I see the insert, and I have three more private functions: display in order, display pre-order, display post-order. I have a feeling it's going to be the same. And if I look down here, I have display in order. Okay, so let's go to the implementation file, and I'm looking at, destroy subtree. There's a search. That's a little bit different than, okay, where are they? Probably at the beginning again, and I missed them. There's insert and insert. There's destroy, there's search, there's remove, delete, make deletion, in order. Okay, so what's happening here? In my main, I called display in order, and I'm passing a node. Const, I don't want to screw it up. If it equals null, I go to the left. Otherwise, I print the value out. Otherwise, I recall going to the right. So check out the order for in order. Left means keep moving to the left. If I can't, because it's false or it's true, depending on what's going on with the if statement. Otherwise, I print, and then finally my other option is to move to the right. So if I come down here to pre, you notice the node is in the beginning, so I print the node. Move to the left, move to the right. Finally post, yep, there it is. I print last, because my node would be, it would go left, right, last. And if we had time, we could sit and draw up a picture and walk through all this, but I think most of you should have a decent understanding of what's going on right now. Yes? Okay.
Yes.
I want you to go and I want you to load up 20-3 while we're here. So I did my inserts, and now I want to search for a number. Okay, in this case, I want to search for 3. And looks like I'm calling here in line 20 a method called search node. I'm sending 3 in to see if it can be found or not. So if it's true that it's found, I print 3 is found. If not, I print 3 is not found. So I'm calling a method called search node. Going back to the header file, I'm looking for search. Let's see, we have search. Let's see, I wanted to check up here first. Do we have anything? Right here, we have search node. Going to the implementation or spec file. We're looking for search node. If anybody sees it, give me a line number. There it is. Okay. So what's going on this time? Boolean int tree, search node, int num tree data. So I'm bringing in a number I want to search for. While, what does line 67 do?
If there is a node or not.
Okay. When would it not be a node? If it would be
No.
null, right?
Null.
So if I keep searching through the tree and I get down to null, then all of a sudden I know I didn't find it and I'm going to return false. Otherwise, I'm going to come inside here. So this time, instead of recursive, I would use a while loop where I'm going to keep moving to the right, to the left, whichever direction I need to go, unless I find it. If I find it, I return true. Otherwise, I keep moving left or I keep moving right till I look for it. Now, this whole search, again, brings in not necessarily when I did the binary search and it was 2 to the n, but this brings in that log base 2 of n, how many levels there are. Does everybody understand what I'm saying? Somebody say
Yeah.
no. Did I get a no from somebody? I don't understand. Thank you. So I'm going to come back over here again and switch over to this camera. So if I had, let's see, 16 items, right? And I had them all laid out. And if I did the binary search, you know, with the 16 items, I'd cut it in half to get 8 items. So I'd go from 16 to 8 to 4 to 2 to 1. And that was my 2, 4, 8. So this would be 2 to the 4th power to guess how many there are right. Okay, that was with 16 items. If I put 16 items in a binary tree, I go, once again, 1, 3, and then the next level was 4, so that gave me 7, and down here to 15. Eventually what we're going to see is this is where that log base 2 of n comes in. It's going to be faster to search than what it was before. We're going to get more into that later. but I just want to make sure as this gets bigger, it's going to be easier to search. It's going to go faster. Let me switch my camera back.
So basically, the compromise here is that it's harder to sort initially, and it takes up a decent amount more memory. However, because of the way it's arranged, it's way easy to search.
Correct. Because remember with the binary search tree, it had to be sorted by one of our sort methods. Now, what we're eventually going to see is how we can sort with this binary tree, and it's going to work out pretty nice. So let me go back to this program. And I think what we're going to do is start with delete on Thursday, because delete's a little bit of a handful and it would be easier if we were in a classroom. What I'd like you to do on your own, and I'm gonna shut down the recording and everything, but this search node, does it look similar to the last 4 things we did that were recursive? Somebody say yes.
As in displaying things?
Yes,
Yes.
as in the in order, the pre-order, the post order, even
Then it is.
inserting. They were all done recursively. What I'm going to let you do, and you still have 10 minutes left of class time, is can you rewrite this search node using recursion? The answer is yes, but I'm asking you to do it. Okay? So I'm going to stop the recording. We're done with class. You can stay logged in if you want, or you can log out. But your exercise for the rest of today is to make this search node function recursive instead of a while loop.
Where
Any
do we,
questions?
Nope.
Any questions? Something for you to play around with. Okay. End of class. Thanks. I'm going to stop the recording.